This video is the first in a series that deals with a branch of chemistry known as chemical kinetics, which is a study of the rates of chemical reactions and how rates change under varying conditions. In this video, we focus on the definition of a rate of reaction, and we are introduced to writing expressions for the rates of chemical reactions directly from balanced chemical equations. Now, we've seen in previous videos in this series how the products of chemical reactions can be predicted from a given set of reactants, and how we can even calculate the amount of products we might expect from a given amount of reactants. And the nature and amount of products formed in chemical reactions is obviously of considerable importance in environmental, industrial, and biochemical applications. However, for most chemical reactions, it is generally equally important to consider how rapidly they take place. For example, let's consider 4 common chemical processes: the combustion of natural gas, the spoiling of milk, the rusting of steel or iron, and the breakdown of plastic bottles in the environment. All of these reactions will take place given the presence of appropriate reactants, but all generally occur at varying rates, from timescales around a millionth of a second up to hundreds or even thousands of years. Now, from a practical point of view, knowledge about the rates of chemical reactions is crucial in food and beverage production, in pollution control, in drug design, and in understanding and manipulating biochemical pathways in medicinal chemistry, as well as in a myriad of other applications where chemical reactions take place. For example, the effect of toxic substances or the effectiveness of pharmaceutical drugs rely just as much on the rate of chemical reactions as they do on whether a chemical reaction takes place at all. As I said, the study of the rates of chemical reactions is called chemical kinetics, and it not only involves measuring or characterizing rates of reactions, but also determining how reaction rates change under varying experimental conditions. And we'll investigate that in some detail as we go forward in this video. The definition for the rate of reaction can be stated as the change in the concentration of a reactant or product per unit time. And the units for the reaction rate are derived from the units for both concentration and time. And there we see molarity per second, or molarity times second to the minus 1 being the units for rates of reaction. Now, since molarity is also the moles of solute per litre of solution, we can also express the rate of reaction in terms of moles per litre per second, or moles times litres to the minus 1 times seconds to the minus 1. Let's consider the simplest hypothetical reaction in which a single reactant A is converted to a single product B. Now, this equation tells us that as the reaction proceeds, A is being consumed and B is being produced. And we can plot the course of this reaction using a concentration time plot, where we see that as A is consumed, its concentration decreases with time, and as B is produced, its concentration increases with time. By convention, we use square brackets around the chemical formula to indicate that we are talking about the concentration of that substance. The rate of reaction for this reaction can be determined from the slope of these curves at any point during the reaction, and this is known as the instantaneous rate, and is determined by calculating the slope of the tangent and by considering the change in concentration of a reactant or product divided by the change in time. And we use the Greek capital delta to indicate a change in concentration, delta B, and a change in time, delta T. Another important measure of rate of reaction that we often want to consider is the initial rate of reaction, which is defined as the instantaneous rate at time t equals 0, and again is determined from the slope of the graph using the change in concentration divided by the change in time. A third measure of rate, and probably the most practical to use in experimental settings, is the average rate of reaction between 2 points in time t1 and t2. And again, we determine the average rate from the slope of the line between these 2 points and by consideration of a change in concentration divided by a change in time. Now we can examine the rate of this simplest of chemical reactions in 2 ways. Firstly, by monitoring the rate of consumption of the reactant A, or by monitoring the rate of production of the product B, and both are equally valid approaches for looking at the reaction rate. And we can write mathematical expressions for both approaches, where we see that the rate of consumption of the reactant A is quantified by the change in concentration of A with respect to the change in time, or that the rate of production of the product B is quantified by the change in concentration of B with respect to the change in time. And again, both of these mathematical expressions are equally valid for defining the rates of these chemical reactions. In these equations, delta A equals the change in concentration of A, that is the concentration of A at time 2 minus its concentration at some time earlier, time 1. The change in concentration of B, delta B, is the concentration of B at some time T2 minus its concentration at some time earlier in the reaction, T1. And delta T, the change in time, represents the time at T2 minus the time at T1. Now you'll note the minus sign in the first of these expressions. Now rates of reactions are always reported as a positive value. You cannot have a negative rate of reaction. In the case of the disappearance or the consumption of a reactant, the concentration will always decrease with time. And because we calculate the change in concentration by subtracting the concentration at some time earlier in the reaction, T1, from the concentration at some time later in the reaction, T2, this means that the change in concentration of reactants is always a negative number. And we use the negative sign to convert the negative delta A value into a positive rate value. So just remember, we'll always have negative signs in front of expressions dealing with reactants. So for the hypothetical reaction A being transformed to B, where the stoichiometric coefficients of each substance in this chemical equation is equal to 1, there are 2 equally valid expressions for the rate of reaction. One referring to the rate of consumption of the reactant, and the other referring to the rate of production of the product. Let's now consider a real reaction where the stoichiometric coefficients have values other than 1. And for example, we've got here the decomposition reaction of dinitrogen pentoxide to produce nitrogen dioxide and elemental oxygen. And we can write valid expressions for the rate of this reaction by considering the consumption of the reactant N2O5, or by considering the rate of the production of one or more of the products. And in this case, we've written down the rate of production of oxygen. So the rate of consumption of N2O5 is minus times the change, or minus 1 times the change in the concentration of N2O5 divided by the change in time. The rate of production of O2 equals the change in concentration of O2 over the change in time. The problem we have in this case, however, is that we cannot simply equate these two expressions as we did above, because these expressions are not mathematically equal. If we take into account the ratio of the stoichiometric coefficients, we can see that for every 2 moles of N2O5 that are consumed, only 1 mole of oxygen is produced. And so the rate of production of oxygen is therefore half the rate of the disappearance of N2O5. To equate the rates in this case, we must take into account the stoichiometric coefficients, and we must divide the rate of disappearance of N2O5 by 2. And that is, we divide it by its own stoichiometric coefficient in the balanced chemical equation. So we get an expression for the rate being minus a half times the rate of disappearance of N2O5. And remember, the minus sign is present because N2O5 is a reactant. Now we can also do this for the rate of appearance of the product NO2, where we get an equivalent expression for the rate as 1/4 times the rate of appearance of NO2. And remembering that the 4 in the fraction comes from the stoichiometric coefficient of NO2. And we can also do it with the product oxygen, where the stoichiometric coefficient is 1, and therefore another expression for the rate of this reaction is equal to 1 times the rate of appearance of O2. So in general, for any reaction, A plus B producing C plus D, where the lowercase letters represent the stoichiometric coefficients, we can represent the rate of reaction in terms of all of the reactants and all of the products by multiplying the rate of disappearance or the rate of appearance by the inverse of the stoichiometric coefficient for each substance in the balanced chemical equation. And remember, when we do this, we must place a negative sign in front of the terms that represent the reactants.